Good afternoon, everyone. So today we have some special guests here from the Society of Peer Mentors going to talk to you for a couple minutes about their program and some opportunities. So I'm going to hand the podium over to them, let them talk for a couple minutes before we get into today's lecture. So welcome, guys.
Okay. Hi, everyone. My name's Zoe. I'm a junior in biological engineering. I'm the vice president of Society of Peer Mentors.
Hi guys, I'm Chloe. I'm also a junior in BE. I'm the membership chair.
Has anyone heard of the Society of Peer Mentors before? No. Some yes, some no. Great. That means we're in the right room. All right. So how do we...
You just hit space right now.
The space? Okay. So why should you join?
So there's three key things that you'll get out of being a mentor for Society of Peer Mentors. The first thing is you get to network. You get to meet students that are in your major and outside your major. You get to talk with other professors that you may not get to talk to on a daily basis. And we also get to talk to people in industry. We'll have people come in and talk at meetings, and sometimes they'll even take people's resume on the spot. They like to see that you're in Society of Peer Mentors.
Yes, we recently had an event yesterday where they were specifically looking for our members to be hired, and it was interlocks. So some of our main things that we do is robotics mentoring. So I don't know if you've heard of the First Robotics League, but basically we send our mentors out to local high schools in the area to mentor them on building a robot that kind of looks like that one for their competition in about February, March. We also help out with the first Lego Robots League. We help them run their competition. It was at the World War II Museum a few years ago. We are known for our Go Engineering Freshman Bridge Camp that we hold every week before school starts. And you get to meet the faculty in your department. You get to do some engineering design competitions, and you get to meet upperclassmen so that you're not lost on your first week of school. We also have our K-12 outreaches with the local Baton Rouge schools. We go to them, we bring them. So like for mechanical engineers, they'll bring like build a car. And so you build a car, or for y'all, it'd probably be like a water filter. And you do the activity with them and teach them about STEM because they probably never heard about STEM before.
Kind of messed it up for you in the
It's
first
okay.
place. There you go.
There we go.
All right, so this is your way of how to get involved. There's a QR code right there if anyone wants to scan it right now. Applications for SPM are going to open October 13th, and deadline, as you can see, is November 22nd. We highly encourage you to apply. It's going to be basically a simple interview process and a resume builder. The sole reason we do the interview process is just to get you guys acclimated to having to go through an interview process. It's mostly just for the interviewees and the interviewers. We're the ones who interview you, so it's not a scary process. It's very simple. Everyone who applies get in. Just letting you know, we highly recommend it.
And also this QR code takes us to our website, spmlsu.org. So if you don't scan it, you can just check us out on our website. So if you want more information, you can contact the officers at spmleaders@lsu.edu, or you can contact me or our president, Caroline, if you have any questions. Right now, if you go on our website, there's a big blue button that's an interest form. If you fill that out, you will be on our email list. So whenever we email about applications being opened, you will be the first in that email list. So if that's something you're interested in, you should definitely go check. And that'll probably have most of the questions that you have. It will be on the website. So does anyone have any questions right now that they want us to answer? No? All right. Thank you.
Thank you, guys.
Yep.
Thank you, guys.
Mm-hmm.
All right, and if anyone does have questions later, I can post this PowerPoint since I've got it from them now. So do let me know if you do want to come back to this at some point. All right. Okay, so today we're coming back again to reactions and reactors. I want to wrap up kind of the what we're learning about them for a moment, and then get into a little bit of practice. And from there, work with Excel a little bit, talk about some data visualization. We'll have a more in-depth Excel session next time on using Excel Solver. Not something that we're going to need on an exam for, by any means, but certainly something that's quite useful, a good skill to have. So I'll try to incorporate that better on future homeworks than I did this time. I did request that you graph some stuff in Excel, and took a problem from the book that I think you need some Excel work for, but I don't think it's, let's see, I'm trying to remember what exactly it was. So, but at any rate, we'll dive in a little deeper next time, and I'll try to make sure I'm ready to discuss the kinds of things that you needed for that homework assignment. But okay, so today talking about mass balances, considering reactions. Last time we did a problem, and I made a note that it might be worth trying it with and without the reaction, because you could get a steady state solution with that CSTR, with pollution coming in, something going out, and you could have that reaction component, which is the problem we solved in class, or you could do it without the reaction component and just prove to yourself that you've got this whole mass balance thing. You could change it around, perhaps create your own problem, say, oh, what if this was a zero order reaction? Of course, the units will have to change, things like that. But think through it in terms of what would it look like if a different reaction order, or if it was growth instead of decay, things like that. So I want to make a couple comments on rate constants themselves. So we have, typically we have some rate, so the rate at which C is changing. We describe that by dc dt. If we're putting that in some volume, then we include a volume term here, and then that becomes a mass per over time term. But just as a rate itself, we'll typically say R of C is dc over dt, and that's described by plus or minus k times c to the n for a given reaction. So we talked about how to incorporate this term into a mass balance. I want to talk for a couple of minutes about the K itself and how we might solve for that, find that, manipulate that, given some problems or given some data. So we'll talk about the half-life. We're actually going to deal with half-life in an example problem today. So what I'll say for now is, assuming we're using a batch case, which that's really the easiest way to determine your kinetics, is do an experiment in a batch container, see how long it takes for your stuff to degrade or to grow, and then you just have your very simple kinetics in, you could say V dc dt is equal to plus or minus k times c to the n power in that volume. The volumes cancel, and then you have a very simple integral to do depending on your reaction order, right? So we did that for zero and second and first order. Not going to really bother too much with first order, but with this, if you remember, let's say the concept of half-life, for example. For half-life, and I'll write this over here. What we're talking about is how much time does it take? So the time until we get half of the stuff we started with. So I'll say time until our ending concentration compared to our initial concentration is equal to 1/2, or 50%, right? That's what we're talking about when we talk about a half-life. So you could solve that. You could say, okay, well, what's the time when these conditions are met? And you can do that, and it turns out to be very easy to do that with the first order decay, which is usually what half-life is, the concept is applied to. If you've ever heard of half-life in terms of the computer game from my era, that's like, a nuclear radiation, issue happens, and we're talking about that. It's called half-life because radioactive materials have a half-life because they're giving off particles and decaying over time, and the half-life then is how long does it take until you started with 1 kilogram and now you have 0.5 kilogram of this uranium or whatever, and it's decomposed into other stuff. So if we remember our batch case for a mass balance for a first order decay, then we've got C over C naught would be equal to e to the minus kt. So really the half-life concept is saying, well, 0.5 is equal to e to the minus k times that, I guess we could call it tau 1/2 or maybe theta 1/2. Tau is often used for lifetimes, so that, or whatever. So, but you get the point. That's our half-life time. Theta is probably not the best setting. We'll leave it as tau. So tau in this case being the lifetime, or the half-life here. And then you can just solve it. Now, if you know the half-life, then you could solve for k. You could solve for the half-life, that amount of time if you know k, or you can solve for k if you know the half-life. Question?
The 0.5 equals e to the negative k. Is that 2 tau 1/2, or is that negative k times tau 1/2?
Sorry, yeah, that's negative k times.
Okay.
Yeah, I'm sorry.
That's okay.
Is it? Thank you. That should be k times the t, and in that case, I was saying that t is half-life, which you could also draw as, I don't know, tau 1/2.
Okay, so just going back to, it was the plug flow reactor.
Yeah.
T equals the different stages. T equals tau over 2, tau equals theta, whatever. What does tau represent there? Does it represent time too?
Okay, so the question is, okay, how does this relate to when we were talking about the plug flow reactors, and we had a graphic that used tau there. So tau is often used for lifetime, okay. And so you can think of it as the lifetime of water that exists in the reactor, so the time it spends in the reactor. So a lot of people will use it interchangeably with the hydraulic retention time.
Okay.
So for our purposes, based on our book's notation, I'm always saying theta is our hydraulic retention time.
Okay, that's how long water stays in the system, right?
Yeah.
Okay, and then it's split up into different parts because, why is it split up into different parts, like T over tau over 2?
So
that's halfway through the system, right?
Yeah, in that graphic, the question is, why is it split up in that graphic into different parts? So in that graphic, you saw tau over 2, or 1/2 times tau. That is halfway through the reactor. Okay. Yeah, that's great. But I didn't mean to be talking about the reactors here when I'm talking about just doing a batch, doing the half-life.
No, yeah.
I wanted to separate these two concepts.
Yeah,
but
no, I would just, when you pointed out tau, I would just...
Yeah.
Okay.
Yeah, certainly that did not mean to confuse you, but there is confusion there because that same tau is used, and it's a very similar concept here. So for the half-life, so I'm specifically talking about you have a batch, or even just like a rock that's decomposing by radiation, whatever it is, that we're just tracking the time it takes for that. The mathematics of the decay, because it's a decay reaction, end up the same, and we can port that into the plug flow reactor. So it's similar systems, but I didn't mean to be talking about this in that context. Okay, all that to say, if we'll see, and we'll do this in a problem, you can set up this arrangement if you know the half-life, or you know some information about the half-life. You can solve, because it's called the half-life, you've got that 0.5 there. It's 1/2, right? Because of that, you can do some solving for k or t as needed. Okay, so that's the first thing I wanted to say about the k. You can relate it based on information you're given. It doesn't have to be half-life. Maybe you're told that it takes an hour until it's 25%. So you could do then 0.25 equals minus k, e to the minus k times 1 hour, right? And then solve for k in that case. So it doesn't have to be half-life, but that's just a common way we do it. So I'm wanting to show you this because for this kind of a case, if our reaction is causing a decay like this, and I say it takes 1 hour, let's pretend that's hours for a moment. Let's say it takes 1 hour until we get I don't know, 33% of our initial, this would be C at 1 hour. Then C at 1 hour divided by C naught is 0.33 in this example. And then we can say that's equal to minus K times T, and we know that T is 1 hour, right? So you could make a mistake here and say, oh, well, if it's 0.33, that means, let's say we started at 100, then it changed by 77 per hour, right? Oh, that's our rate, but that's not true. That's treating it as if it was a linear drop from here to here, right? And then that would presumably go down to there. And so really what that would be, you might make that mistake, but if you were to really write it out that way, it should be 77 units per volume per hour or something, right? Because that's actually what you physically just showed by drawing that line. Okay, so I'm saying this because there can be confusion. We'll see it in a problem in a minute. Hopefully that'll help make it clearer. You don't want to just assume that because I told you something that it dropped like that it just immediately went down. Okay, you got a question?
Yeah, no. It says e to the negative k. What's after? Yeah.
Times 1 hour.
Oh, okay. Okay, cool. All right, that's it. Thank you.
Okay, and I was just sort of ranting here, so I didn't mean to. This is not exactly what I wanted to be showing with this stuff. So I'm going to erase this. You can always find it back on the video recording if you wanted to go through that rant again. What I really wanted to show you was when we're considering a system like this, let's say a first order system, and we want to get the kinetics, what we need to do, if we just got the data, we need to use that data to find K, is we need to linearize the data. So right now we have it as C versus time, concentration versus time, and it's going to look like this if that's a first order decay. And we can't directly extrapolate the K from this graph, right? That's kind of my point of what I was jabbering on about. If it was linear, then you could get it, because that slope of that line is going to be K, but this slope changes over time depending on how much stuff we have in there, so it doesn't work. So we need a way of linearizing it, and that's going to be going from this C equals C naught times e to the minus kt to taking the natural log of both sides to get rid of that exponent, right? So then we can take natural log of C equals natural log of C naught times minus kt. Or we could write this as the natural log of C over C naught equals minus kt. So that form is linear, but that means our y-axis has to be a natural log axis, not the generic C here. So to do that, we can take our data and transform it. Instead of plotting C, we plot the natural log of C over C naught, something we'll do in Excel. So then what we'll have, if it's a first order, is we'll get our data points in some nice linear trend and can draw our line. Whereas in the previous case, that was a bad line, but you get the point. Previous case, our data points would be something like this, and even if we do a line of or an exponent of best fit, we don't have a direct way of getting at the K. Whereas in this case, we do that regression, then we can get K based on the slope here. Okay, because then it's y equals mx plus b, and a lot of times we're going to start at 0, so there's not even a b. That's going to happen because when we take a look at natural log of C over C naught, if you take the natural log of 1, what to the power, so anything to the power of what equals 1, anything to the power of 0 equals 1, right? So when we're solving that natural log at this start, at our initial time point c is equal to c naught. So the very first data point is our starting point, so c equals c naught. Every point after that, we have a new c, but we're keeping that c naught. So then natural log of, c naught over c naught, that's equal to the natural log of 1, which is equal to 0. Right? It'll make more sense when you look at it on a graph or whatever. But that's why we have it intercepting at 0 there, and that's why b will go to 0, and it just becomes even a little bit simpler. Okay. Okay. So then let's take a look at what that might look like in Excel. And we'll come back to Excel for some more fun in a minute. So let's get rid of this for a moment. Okay, so I took some data from some sort of example, and over time, in minutes, we have some concentration of a pesticide being destroyed. This is in micromolar units, and so we start off with quite a bit, and it's degrading. And so if you plot that directly, you see, our data points are falling in a pretty exponential decay sort of a manner. So that's exactly kind of what I was showing. Now, if we take this and we do that natural log transformation, what we can do, so I wrote here ln of c over c naught, we can just say equals ln, parenthesis, and then the initial concentration here, the first where we started with, divided by that same one, and then here I'm using the, I don't know if you can see that. I'll try to increase my font or resolution next time so that you can see it better. But I put the little $sign so it freezes that right there for that second term. You can see adding or having the $sign or ignoring it. Putting it there means it's going to keep it that way throughout the whole thing. So when we fill it downwards, it stays at B3. So this next one, the second one, is saying, okay, well, at time 15, the concentration, we'll take the natural log of that divided by, again, that concentration at time 0. So like I said, it's just this natural log transformation. Each of these gives us a new point based on that initial divided by, or the final divided by the initial. So when we do that, then we get the graph that I moved out of the way. And we get a plot here that it's intercepting at 0. And it's a nice linear line. We can add this linear regression, and we get, if we put the equation on the chart, we see a pretty nice r² value, and we get this y equals minus 0.0643 times x. So that's our slope right there. That's our k for this problem. All right, does that make sense? Okay. Cool. All right. So with that, let's do a couple practice problems. Won't need Excel here. We'll come back and take a look at some data visualization in a few minutes. So here's a problem regarding a smoky bar. So a bar with a volume of 500 cubic meters has 50 smokers in it, each smoking 2 cigarettes per hour. An individual cigarette emits, among other things, about 1.4 milligrams of formaldehyde, HCHO, which then converts to carbon dioxide with a reaction rate coefficient K equals 0.40 per hour. Fresh air enters the bar at a rate of 1,000 cubic meters per hour, and stale air leaves at the same rate. Assuming complete mixing, estimate the steady state concentration of formaldehyde in the air at 25 degrees Celsius and at 1 atmosphere of pressure. How does the result compare with the threshold for eye irritation of 0.05 parts per million? Okay, so there's a lot going on there. So go ahead and see if you can start this and approach the problem and take some good first steps. We definitely draw the system as one of the starting steps. Okay, so hopefully you're taking a look at this problem, drew something up, identified what you know, what you don't know, and one thing you hopefully noticed was, okay, well, it's at steady state. If we write a mass balance, we can say that 0 equals what's coming in, which is fresh air, so it has no formaldehyde. So that should be Q times 0 minus what's going out, QC, plus the fact that we're generating stuff from the smokers inside. And then we notice we actually have 2 reactions in here, so then we have a minus the decay of the formaldehyde in that volume. Okay? And it's acting, it said I think it said it's well mixed. Kind of assume that with that much flow rate coming in and it's just sort of a room, you could assume it's a CSTR, so that kind of makes sense that way. Oh yeah, it says complete mixing, so that's the tip off for the CSTR. Okay, so that hopefully is a starting point. And one thing I did here was I wrote, and I'm not, I'll take a look at the book solution here because I haven't actually looked at this one before. It's 140 milligrams per hour is what they gave for the amount of formaldehyde being added, and that should be able to go directly in here because our accumulation terms are all going to be mass per time, right? So maybe we need to convert those units, but should be the case that we can use hours because everything else is in hours, and a mass there should work out because Q times C gives us, at the end of the day, some mass per time, right? So the fact that it's just given as mass per time, we don't even need to worry about the reaction there, like the reaction term. We just know that that is the total stuff being produced, right? And that I got that from looking at the units, right? I didn't have to look for a K for the reaction that's adding the stuff, the smoking that's adding the stuff. It's you could also look at it as another input rate, right? Instead of a reaction rate, it could just be one of the input rates here. Okay. At any rate, that should be a good start. I'll let you carry on for a couple more minutes. if you take that approach, and by the way, I'm sorry, I was looking at the figure that they drew in the example, and they had already put the 140, so I thought, you know, I didn't realize I should have specified where that comes from. Is that 2 cigarettes per hour times 50 people smoking times that 1.4 milligrams of formaldehyde per cigarette. So multiplying those together gives us that rate of addition. I guess another input rate there that we add. Okay, with that, then we can solve this mass balance. We get the C's on the same term, so we can solve for C. So QC plus VKC equals 140. Can simplify so that C is equal to that 140 divided by Q plus VK. And assuming we've got everything in meters and hours, then that turns out to be 0.117 milligrams per cubic meter. Now, to do the final part of that question, we need to compare and convert that milligrams to parts per million. We are also given the 25 Celsius and 1 atmosphere of pressure, so pretty much standard conditions there. So we'll need to convert this into parts per million. So just as a refresher, see if you can do that part. We can say H is 1 gram per mole. C is pretty much 12 grams per mole. Oxygen is basically 16 grams per mole. So we could go back and look it all up with R and do the solution for the PV equals nRT. We'll need that relationship here in order to convert to parts per million. But I'm just reminding you here that we solved in the past that at 25 degrees Celsius, 1 atmosphere, there's 24.465 liters per mole of an ideal gas. We'll treat it that way. Okay, so the solution that the book provides says we can just take that concentration here in milligrams per cubic meter, multiply that by the liters per mole, divide that by the molecular weight, so that 30 grams per mole, and what they're not showing here is the conversions between milligrams to grams from liters to cubic meters and satisfying all of that, and then giving it in terms of parts per million. So the book sort of hides all that, and we're just assuming that all of that works out properly. But if we get it all appropriately into molar terms, then that molar fraction, what percent of the 1 cubic meter is moles of HCHO, that gives us our answer. So the final answer they provide then says the concentration is 0.095 ppm. So it's a little more involved. We've already covered that stuff, all those conversions, so I'm not spending much time on it. That's their final answer, and that's almost double that regulatory standard there that says, at even about half that, you'll get eye irritation from formaldehyde. Okay. Any questions, issues with that? So this is, at the end of the day, this was a complicated CSTR, had other stuff going on in it, but it was a CSTR with a reaction, and instead of having a flow bringing in stuff, it was just that cigarette smoke was providing stuff inside. Okay? Same principles of the mass balance applied, so when we took that approach, we were able to get an answer. Okay, so here's a plug flow reaction we can take a look at. This will be also a little bit different, but hopefully useful for you. So every year, herons, seagulls, eagles, and other birds mass along a 4.75 kilometer stretch of stream connecting a lake to the ocean to catch fingerling salmon as they migrate downstream to the sea. The birds are efficient fishermen and will consume 10,000 fingerlings per kilometer of stream each hour, regardless of the number of salmon in the stream. In other words, there are enough salmon. The birds are only limited by how fast they can catch and eat the fish. The stream's average cross-sectional area is 20 square meters, and the salmon move downstream with a stream's flow rate of 700 cubic meters per minute. If there are 7 fingerlings per cubic meter in the water entering the stream, what is the concentration of salmon that reach the ocean when the birds are feeding? So the birds are taking out stuff in this plug flow reactor, the stream that's acting like a plug flow reactor. Doesn't matter really to the birds how many are there. They're just taking what they're going to take, and they're just constantly taking it. So I'm going to write these out on the graphic a little bigger so you can hopefully see them better that way. I'm going to do a little bit of a close-up on this stream, by the way. We're talking about this stream. It said the length was 4.75 kilometers. And then it said the cross-sectional area. What it's talking about is we have some depth to the stream, and we're just looking at that cross-section. That's what it's talking about. So it's like taking a pipe that's long and then looking at what's the area inside that, on that cross section there. So that area is 20 square meters. Yeah, so if you imagine you have a stream flowing, and it's 5 kilometers long, practically, then you want to know something else about like how much water fits in there. You'll need to know the cross-sectional area, meaning, so it's really long, and then you take like a slice of it and say,
So
well, what's the
20 meters long, 10 meters deep.
Yeah, it could be that it's
Or
1
10
meter
meters
deep,
long and
20 meters
Or
wide, and 1 meter deep,
Yeah, okay.
and
So that's-
it
okay.
stretches for 5 kilometers, right?
Okay, that makes sense.
Yeah, that's all we're talking about there. So it's a lot of times for a system like this, you'll be using like a pipe or something, and you'll need the area of the circle that the pipe makes, and then the length of the pipe. So we're basically doing the same thing here. So you can get some volume for the stream. Okay, so the rate constant here for fish removal is a little tricky. It's one of the reasons why I wanted to show this one. This is not Half-Life 1. I was thinking of a different problem, so sorry about that. Maybe we'll take a look at that problem too. But here, we've got the K. We're trying to know something about the K. We were told the birds are going to eat 10,000 fingerlings per kilometer of stream. And so I botched that here. Per hour, regardless of what's in there. Now, the fact that they said regardless of what's in there, that should have clued you in that, hey, this has something that maybe triggers some memory of, that has something to do with the rate order, right? Because when we talk about rates, zero order versus second order versus first order, that depends on, the question is how does it depend on how much stuff is in there? And in this case, it says it does not. And so that means K is going to be zero order. Because, first of all, it says regardless of the number of salmon. And second of all, the way it's written, it's some number of fish per 1 kilometer, so that's 1,000 meters, in the stream per hour. So because the stream is it has that cross section of 20 square meters, we can get a volume. So this K would then be some number of fish per volume per time. And that unit corresponds to the units for a zero order reaction, right? It's the mass or number per volume per time. So our rate equation, we'll say of C dt, is going to be negative K times C to the 0 power because it does not depend on C. So it'll just be negative K, and that'll be our rate term. We can then put that into our equation. Okay. So with that, I'm going to go ahead and just keep the drawing here for a moment. Actually, I don't think we need that much space. We'll go from here. So with that, we can solve for this K, and that becomes, I'm going to get rid of this. K becomes 0.50 fish. So half a fish per cubic meter per hour. If we solve that. Okay? Yeah.
Where did you get the 1,000 meters from?
Good question. So the 1,000 meters came from the per kilometer here of stream. So again, it was a tricky word problem here, but it said they've removed 10,000 fingerlings per kilometer of stream, and so that's where that came from. And I even wrote that wrong when I first wrote it up. I wrote they're removing that much from the stream, and then I had to come back and correct. Okay, so with that, then we can treat this as a plug flow reactor with a zero order reaction. So it's rather simple. We're going to treat it like a batch reactor that just stays in that chamber for some amount of time. And that time is going to depend on the volume there. So let's go ahead and solve that volume. That's going to be the 20 square meters times 4,750 meters. So the volume term comes out to be not written up here. So we're going to do that real quick. So we'll take that 20 times that 4.75 kilometers. That's correct, right? Yep. So the total stream volume is 95,000 cubic meters then. We can get a theta, it's V over Q. So we'll take that 95,000, divide it by the 700 cubic meters. Let's do that again real quick. So the flow rate was 700 cubic meters per hour. I'm sorry, that's per minute, so we need to change that. So we'll have to divide that by, or I guess that gives it to us in minutes. So let's divide that by 60 for doing it in hours. So 2.26 hours. I've got that right. So then when we set up our mass balance, we'll be saying that our...
So that's how long, 2.26 hours is how long it takes for that section of water to move through, right?
Yeah, so just for the people online, that 2.26 hours is how long it takes for, if you were to drop a buoy or a bobber or something in the water at the lake right when it enters the stream, and you track it, it flows the same flow rate as the water. It takes 2.26 hours for that buoy to exit and make its way into the ocean. And that's our hydraulic retention time. Okay, so then when we write up our mass balance, we can say, considering it like a batch reactor that's just going to be in there for some amount of time, it's going to look like that. When we integrate, we're going to have the integration of dc from c naught to c equal to the integration of minus k times dt from 0 to t. That's going to give us c minus c naught is equal to minus k. And instead of t, we're really just going to go to theta, right? Minus k times theta. Okay, so that's relatively straightforward there, and we're solving for c. So c equals c naught minus k theta. And if we take a moment to take a look at the units, we're expecting, since the fish are being removed, that the c entering the ocean should be less than c naught. And our equation here has a start at that initial point, and we're subtracting something from it. So presumably that means we're removing stuff, so that's good. And it should, what we're removing, the k theta, should be in terms of that concentration. And our concentration was fish per cubic meter. So if we take this 10,000 fish per cubic meter per hour, multiply that by those hours there for theta, then that should work. So in the end, when we solve for c, that should give us 5.9 fish per cubic meter. Okay, yeah.
Did that without any integration or anything like that? I just got the rate of finger that was like killed an hour, and then plugged that into that raw equation. Is that acceptable too?
Yeah, so for those online, there was a question about somebody did this without any integration or anything like that, and just solved that rate and kind of just, essentially you did it without the elaborate mass balance part of it, I suppose, and you just treated it like a typical word problem that you could solve without knowing anything about this class. That's fine in this case. What we see here is because it's zero order, that works just fine and it's pretty simple. What I will caution you is just make sure that you're comfortable doing it the elaborated way in case there's some different inputs or outputs or other stuff going on. It takes, a word problem like this you could probably do without any calculus, right? But if it gets more complicated, then you might need it or might benefit from this approach. So yeah, that's fine, and I wouldn't count that against you either. All right, any other questions or issues? Okay, so I want to take a few minutes, since you've got at least one homework assignment that requires you to graph stuff in Excel or something similar. And I want to just talk briefly about data analysis and visualization from kind of a, I guess, a sort of a professionalism approach. So you're going to be happy with yourselves if you improve on your data visualization skills. No matter what you do in life, that's going to benefit you, right? So how many of you, by show of hands, think that's an ugly graph? Okay, some of you are not really being honest here, or maybe not awake. That's a pretty ugly graph. And in fact, when I took the little screen capture, I intentionally just like caught the the boundaries and the edges there. It's all nasty. Compare that to, how about that graph? That one's a little better, huh? So, and to be fair, I didn't make that one in Excel. So, I used some software that's sort of designed for making nice graphs. But what I wanted to show here is the impact it has, and if you were to like track the different things wrong with this graph compared to what you might think are right with this one, you'll actually find quite a few. Right, this one is readable. You can actually see the numbers. I prepared it for a presentation, so it's big enough. It's not like it's some tiny font that's going into a paper or something. Even then, it hopefully is readable, but at a different scale than on a PowerPoint slide. It actually has axis labels, right? Those are also readable. It's got these nice little tick marks instead of the grid lines, which are distracting. The symbols are large enough. It's got a nice little outline. There's a lot of little tiny things about it, right? So when we go to Excel and we want to, draw up something that's meaningful, there's a lot we can do that's better than just the Excel default. Now, I'm not going to be too harsh on you or whatever for your Excel work, but I am going to ask you to improve beyond the generic, right? So the very base generic, here's the graph that I grabbed, and I went ahead and took a screen grab. If you didn't know, at least in, well, that's not very helpful. At least in Windows, you can do the Windows key Shift and S, and then draw a spot. Sometimes that's handy, but and then I could paste that somewhere, and it's just basically a picture of what I just did. However you want to do it, you could import it directly. My point here is that this graph needs a lot of work. So if we were to take this in Excel and work on it, first things I would say is we need to make sure that it's communicating, right? We need to make sure we've got the target audience in mind in terms of how big it needs to be or whatever. But ultimately, we want to make sure we're communicating with the graph. So this one here doesn't communicate much at all because who knows what the y and the x axes are. So it'd be much better to at least have it labeled in some way. I'm sure you guys all know how to do this stuff or will figure it out with no problem. I'm just going to run through a few things just to make the point. We would need the x-axis label, need a y-axis label. I wouldn't want to just leave it at that. Maybe bold it, maybe increase the size a bit, maybe do the same for these other axes. You can do most of the, most of the same shortcuts, hotkeys, and stuff that you might use normal circumstances. You can just select it and do that. So what I was doing there was Control shift, and then the greater than or less than sign makes you do bigger or smaller font. And then I did Control B when I highlighted the stuff to make it bold, stuff like that. Now, most scientific documents, reports and stuff don't actually label the graph with like a title, a graph title, like Excel sometimes will do. Instead, you'd have a figure caption below it. For our class, it doesn't really matter too much to me. If you needed to display multiple, I would expect one or the other so that it was clear. I'd probably expect some sort of a legend here if there's more than one thing. I don't particularly love the little grid bars. I do like having the axis bordered on all sides. That is possible in Excel, although it's easier in another program that I like. So we can go through and add those, and I think you can even add the little grid markers you see here. I think you can do that in Excel as well. It just takes a little bit of work. You fuss with it, you do stuff with it, and at the end of the day, you can get a much more attractive graph that's going to be much more persuasive for whatever you're trying to do or sell or convince somebody with. You're going to communicate a lot better with that. And those are all great things. So at the end of the day, what I would encourage you to do is be thoughtful with making sure you're communicating, you're eliminating noise. So what I just did, getting rid of those grid lines, that's just a bunch of extra noise, right? So I deleted those, focusing on specifically what it is that I want to highlight. Maybe I would increase the size of these. If I've got more than one plot here on my graph, I'd want a legend to differentiate them. There's also something that you might see or you might be tempted to do fairly often with a graph like this, and that would be to have, instead of a scatter plot like this, to have a line graph. I think I can show that better in my other program. A little quicker. Same thing goes for Excel. This is just a cool program. I can tell you more about it later if you want. But you see here I've got a plot, and each of these has a line drawn between the points. I don't normally like that. And the reason is because that doesn't convey much unless you're trying to keep the dots separate. So if I wanted to make sure it's easy to see that these triangle ones are lower than these diamond ones, those little lines kind of help a little bit. But otherwise, if it's just the connect the dots type of thing, you might as well get rid of it and add a trend line if you do have a straight line, right? So when you're in Excel and making a new graph, I would encourage you to use the scatter instead of these ones with the squiggles, because we're not playing connect the dots. If we want to evaluate a trend, we're going to do it with a trend line, right? So just a couple thoughts there for you. Occasionally it does make sense. Maybe if you have a whole bunch of points and all in a nice little curve and you want to smooth that curve, maybe that makes sense to do a smooth line. But a lot of times, especially with kinetics analysis, just do that scatter and then use a regression of some sort as needed. Okay, so any questions or thoughts in that regard? Okay, next time my plan is to give a little bit better of a demo on using the Excel solver to solve for some problems, maybe with a case where we don't have a good derivation of a mass balance. We have to use something funky, and we have to use maybe reiterated guesses to get there, some stuff like that. I'll try to get some good examples for that, and we'll take a look at that next time. All right, that's all for today. See you guys on Thursday.
having like a ton of trouble understanding what we're doing. And by the